In this video, I'm going to show the image of why you prefer NRZ SerDes. Let's understand what the NRZ data is in a SerDes system. The non-return to zero data format is a pulse amplitude modulation 2, or called PAM4, which means 1 bit per symbol and 2 voltage levels. A quick reminder for you is that a symbol is used to make 1 bit or more than 1 bit and is used to transmit bits over a channel. As you can see, any symbol is exactly mapped to 1 bit in an NRZ format. Logical 1 will stay at the voltage level V during the T-bit bit duration time. On the other hand, the logic 0 will stay at the voltage level 0 during the T-bit bit duration time. So, the NRZ bitstream 011010 would be the symbol pressed at different time slots during the 6-bit time sequentially. If you chop the bitstream with every 2 bits time over 2 unit intervals 2 UIs, then overlap them to get the I diagram as shown here, which will help your signal integrity analysis. After understanding the non-return to zero NRZ, do you think we have the opposite one called return to zero RZ data? What does that look like in your images? Yes, the RZ data is possible, and it is almost the same as the non-return to zero data, except to the symbol 1. As you can see, the logic 1 will stay at the voltage level V during 1/2 bit duration time and return to the 0 for another 1/2 bit duration time. Again, you can apply a similar way of getting the RZ bitstream and the I diagram. Any comparison image of both RZ and NRZ you have so far? Think about your own images for 5 seconds. Good. Here are your time domain NRZ versus RZ images. Do you see any obvious difference between both bitstream and the I diagram? Bingo! In the bitstream, the RZ data's number of transition is greater than the NRZ data's number. In the I diagram, the transition time of the RZ data is half of the NRZ one. So, which one is better in terms of bandwidth or circuit images? Or which one has a smaller bandwidth? What does a greater number of transition or shorter transition time in the time domain mean? Think about the time domain images for 5 seconds. Bingo! That means a wider bandwidth in an RZ data format. Why? A shorter period means a higher frequency, or the frequency is an inverse of the period. So, as you can see, the ballpark 3 dB bandwidth of RZ is twice of the NRZ. Which one do we prefer in terms of the circuit image? Correct. We may prefer NRZ owing to its low bandwidth property, which will simplify the SerDes design and achieve a low power at the same time. Alright, if we prefer the NRZ SerDes, what else we can reduce the design challenge and improve the link quality at the same time? Correct. The NRZ's DC level or reference level can be simplified further. As we discussed in the wide differential video, we will mention the single-ended data was not preferable due to the complexity and design challenges. Instead, the differential signals would be simple. For example, the reference level would be a ground reference, which could be as simple as possible without any big issues. Also, the zero DC can allow the AC couple under a careful design between the TX and the RX, such that both can achieve the best signal integrity respectively. Instead of the RZ, Do you have other data image we can try? Think about your pulse amplitude modulation image one more time for 5 seconds. Right, we can further increase the voltage level from 2 to 4, which is a pulse amplitude modulation 4, or called PAM4. But why would you do that? Think about the bandwidth images for 5 seconds. Yes, any symbol could be encoded or mapped to 2 bits by extending to 4 levels as shown here. Therefore, the PAM4 symbol duration is twice the NRZ symbol duration in the time domain. In other words, the PAM4 symbol rate is half of the NRZ symbol rate in the frequency domain. At this moment, you may say the PAM4 is better than the NRZ, while you already had the bandwidth image, right? Bingo, you are correct that the PAM4 is preferable owing to its low bandwidth requirement. But remember, the circuit image could be your main consideration. What's the goal of the SerDes you like to develop? Simplicity and low power for whatever circuit images, right? What are the circuit images of both NRZ and PAM4? As you can see, the TX driver's maximum output swing VTX will be limited by its supply voltage VDD. Regardless of the circuit images, both PAM4 and NRZ I shows a 1 volt maximum peak-to-peak output swing here. Ideally, the minimum I high of the PAM4 between symbols is 1/3 of the I high of the NRZ. So, the PAM4 would have a 9.5 dB worse noise margin than the NRZ. To achieve the required bit error rate, reducing the circuit noise by increasing the PAM4's TX power consumption would be necessary. In addition to the noise, any circuit image you may have to consider are the TX output. Correct. For PAM4 TX, generating the PAM4 output signals with good signal integrity is very challenging, even though the concept is straightforward. For example, the NRZ driver's 3 segments would be split into 2 segments for the MSB DIN 1 and 1 segment for the LSB DIN 0 for PAM4's every 2 bits. The PAM4's driver is like a simple 2-bit stack, and the linearity requirement is very strict. Any PAM4 I diagram image would be your concern? Bingo! Unequal I high between symbols could be an issue. Ideally, the I high is the same between symbols. Therefore, the noise margin can be maximized, and the bit error rate can be minimized. But the mismatch between 2 segments and 1 segment drivers will create different I high between constitutive symbols. For example, symbol 10 is closer to the decision threshold VREF1 than symbol 11. Therefore, symbol 10 has a less noise immunity, and a decision maker is more likely to be mistaken to symbol 11, which limits the bit error rate. To improve the mismatch or linearity, the PAM4 TX driver size must be increased, and that will cost more power than the NRZ TX. In addition to the I high, what are your TX I width image of both PAM4 and NRZ? Think about your own circuit images for 5 seconds. Yes, the PAM4's I width degrades much worse than the NRZ I width due to the multiple crossover effect. As you can see, the NRZ single crossover makes the determinist jitter near 0 across the reference level. But the PAM4's multiple crossovers cause the non-zero determinist jitter as shown here, even though the transition is very sharp. If the data transition is getting slow, the jitter or I width will degrade much quicker in the PAM4. Think about the PAM4's multi-crossover eye width image on your own to get more ideas about it. After the TX, what are your RX circuit images of both PAM4 versus NRZ? Correct. All the PAM4 TX circuit impairments will show up at the PAM4 RX as well. For example, the PAM4 RX would have a 9.5 dB worse noise margin than the NRZ RX. The best signal integrity must also be maintained at the RX side as well to keep equal eye height between symbols and minimal deterministic jitter. So, the RX is like a 2-bit ADC under an analog approach PAM4 system as shown here. But the RX is much more challenging to maintain the linearity and bandwidth due to the unknown TX output swing, unknown channel, etc. What can we do? Think about your circuit images for 5 seconds. Bingo! As we discussed in the white adaptation video, under unknown TX output swing and unknown channel, the RX front-end amplifier's linearity can be maintained by a few VGS with side-side LMS attachment. Even though the attachment can keep the PAM4 to have an equal eye height and eye width under a good linearity, this is still very challenging and power hungry. Similarly, to maintain the bandwidth without knowing the TX FFE and channel loss, both attachment of the CTOE and DFE are necessary. Again, those attachments would be too complicated to reduce the power. Not to mention other DSP assistant PAM4 SerDes would be much more power hungry than the simple analog circuitry we present here. Lastly, those PAM4 TX and RX circuit images may explain why you would stay with the NRZ SerDes, even though it's a higher symbol rate or bandwidth. Here is the summarized image you may have for why you prefer the NRZ SerDes. Obviously, the circuit of the NRZ is easy to generate the logic 1 compared to the return to 0. In addition, the bandwidth or speed requirement of the NRZ is less than the RZ SerDes. Again, the NRZ TX is easy to generate 2 levels compared to the PAM4's 4 levels. The NRZ RX can detect the 2 levels simply with ground reference differentially, compared to the PAM4's 4 levels with 9.5 dB less motive margin. Also, the jitter margin would be less in the PAM4 as well. So, the NRZ is preferable with a simpler circuitry and lower power than RZ and PAM4 SerDes. Lastly, not only the signal bandwidth, but also the circuit simplicity would be your best circuit image, since that can achieve a low power and low bit error rate at the same time easily. Thanks for watching. Before you go, if you're benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share your video link with people who may benefit from it.